Hi everyone. In this video I'm going to talk about losses in an induction motor, also called an asynchronous motor. To explain this properly, I will first explain a little bit more about how an induction motor works. In the stator of a three-phase induction motor, over here there are three coils, shifted 120 degrees with respect to each other. And these coils generate an electromagnetic field that rotates in the stator. This field can be thought of as a fictitious magnet rotating in the stator at a constant speed which is equal to the synchronous speed ns. This synchronous speed is linked to the main frequency, which is 50 Hz in Europe. So in that case the synchronous speed is equal to 3000 RPM, rotations per minute. So now what happens if a coil is added to the rotor in that rotating magnetic field? So that coil is experiencing a changing magnetic field. So due to the changing magnetic field, a voltage is generated in that coil, which we call the induction voltage, also known as the back EMF voltage. And what we want to have is that a current will flow in that rotor, because when a current flows in the rotor, Lorentz forces are generated, and in that case a torque will be generated. But in this situation a current can't flow because this is an interrupted coil over here. So what we need is a short circuit in that coil. So when we short circuit it, a short circuit current can flow, and due to these currents Lorentz forces are generated, and therefore a torque will be generated on the rotor, so the rotor starts turning, rotating. Right, so how does that work, that rotating field in the stator? So we have here the three coils which are situated 120 degrees separated from each other. And what we see over here is that we have three voltages applied to these three coils, and also these voltages have a phase shift of 120 degrees. So let's look to this situation in which the voltage through phase A is at its maximum value, which is a positive value in this case, at this point, and the voltages at coil B and coil C have half the value and in the opposite direction. Now we can draw the flux vectors, and the flux vectors are drawn over here. So the flux in coil number A, which is this coil, has a maximum value in this direction. The flux in both coils B and C have the opposite direction and half the amplitude. So when we add these flux vectors together, we get a total combined flux vector in this direction, which is 1.5 times the flux vector of the flux in coil number A. So that is the situation over here. When we look 60 degrees further, so at this point, then we see that the voltage in coil number C has the maximum value, but it's negative, so it generates a flux through, towards this direction, and the voltages through coils A and B have half the value in the positive direction, so in that direction, and they have half the value. So the total flux in this case is also in this direction and has 1.5 times the flux value generated by the flux in this coil over here. So that is the situation at 60 degrees. And of course that happens all the times, at every change when we shift here in the angle around the stator. So when we see what happens over there is that at every point at the circumference of the stator, the flux is has its maximum value, 1.5 times the flux of one coil, and has a constant value. So at every point my flux, so my torque, has a constant value, and that can be shown over here when we have this animation. And you see here the stator over here, and the flux vectors varying, and the black one is the total flux over here, which has the maximum value of 1.5 times the maximum flux through one phase. So alright, so that is how a asynchronous motor or an induction motor works. So now let's look to the power balance, and here we have the input voltage towards the stator, so towards the coils in the stator over here. So that is the active power to the stator. We call that PE, the electrical power. And as we said, in the stator there are 3 coils and they are made of copper, so we have copper losses, also known as I2R losses over here. And these coils are situated in the stator, which is made of iron, so we also have iron losses. And the input losses, the input power minus the copper losses minus the iron losses is the active power which is supplied to the rotor, which makes the rotor turn and which is available for generating the output torque. But as you know, the coils in the rotor are also made of copper or of messing, brass, or something which can conduct electricity, so we have I2 losses also in the rotor. And these conduction losses, these I2R losses in the rotor, are proportional to the slip. And this slip is the difference between the speed of the rotating field in the stator and the speed of the rotor, divided by the speed of the rotating field in the stator. So there is always slip in an asynchronous motor, because when the rotor has the same speed as the rotating field in the stator, the rotor does not experience a changing magnetic field, so no voltage is induced in that rotor, so no currents will flow, no Lorentz forces are generated, so no torque is generated. So there is always slip in the rotor, and there are also in that case losses in the rotor due to that slip. And when we subtract the losses in the rotor from the active power supplied to the rotor, then we have the mechanical power which can be used for torque generation. But there are also windage and friction losses over here in the motor, so the actual shaft power PL is the mechanical power PM minus the windage and friction losses. So written in equations, we have the power across the air gap, which is equal to the input power PE minus I2R losses in the stator minus the iron losses also in that stator. We have seen that the copper losses in the rotor are equal to the active power supplied to the rotor multiplied with the slip. So in case of a locked rotor, we have 100% slip, so the complete electrical power is dissipated in the rotor. So you never want to have a locked rotor for an asynchronous motor. And we see that the mechanical power PM is equal to this active power supplied to the rotor minus the I2R losses in the rotor. So it's 1 minus S times PR. And of course the shaft power PL is equal to the mechanical power PM minus the losses over here, the windage and friction losses. So we can also define the efficiency of a motor, which is equal to the output power, which is the shaft power PL, divided by the active input power PE and multiplied by 100%. So that is the efficiency. So summarized, we can conclude that the copper losses in a rotor are determined by the slip over here. And when the rotor is locked, so when the slip is 1, the total power across the air gap is converted into heat of the rotor. That's all about the power balance and dissipation in the asynchronous motor. Thank you for watching.